was around there until like 10 years ago now.
Right. Well, I left a bit. I think I left. Well, I've been here in this address. Yeah, I must have left there 30 years ago, but grew up there. So maybe that was after you were, or maybe you were. I don't know. Were you about at that time in the 80s? Flight 3, Zulu Delta Zulu, Golf 2, Foxtrot Tango.
Yeah, wow. Golf 2 XC. Thank you for calling in and good afternoon to you. You nearly broke my meter.
Well, hello there. Nick the Vic here, M0NTV, and welcome back to my shack. Good to see you. Well, I wanted to do a video today to kind of just bring you up to speed with where I'm at in my home brewing adventures, and to share some details of my most recent homebrew radio that I finished just before Christmas. I've been building this thing for months really, but Christmas Eve I just finally got it boxed up, as it were, and it's something I've been wanting to do for ages. It's the third scratch-built transceiver that I've made, but this one is very different because this one is a software-defined radio. There's all kinds of stuff to explore, you know, not just with the physical construction of it, but with the code and how you make that work as well. Now it's called the Really Useful Rig. So cool because it's built in, guess what, a really useful box. Now I can hear some people already thinking, what? He's built a radio in a plastic box, you know, because it is a risky thing to do, because you've got no RF shielding in the chassis at all, and you have to be a bit creative about how you're going to get ground in there and other things as well. Now actually in my rig there are individual, it's a very modular construction like most of my stuff, but probably even more so this time, and there are individual modules in there that have some RF shielding. But no, true enough, the actual whole thing doesn't. Seems to work okay. Jury's still out a bit, really. I'm not sure whether I'd do it again quite like that. But anyway, I thought it was worth giving it a go. Charlie Morris builds rigs in plastic sandwich boxes, so I thought, you know, it's worth a bash, isn't it? Worth a bash. I'll show you the rig and you can decide for yourself. Okay, so what I've got is I've got a bit of a kind of walkthrough of the rig itself, and so you can kind of see, you know, what it's made up of in terms of the hardware, and a little bit on the software, a little bit of theory as to kind of how it kind of works. But if you're not interested in any of that stuff, that's fine. You might want to fast forward to the end of this video where you can see a bit more on the air testing. So there's a little bit more of me kind of tuning down the 80 meter band and a QSO. So it's only a little rubber stamp 5.9 QSO, but it proves that it works. And anybody that's frequented 80 meters will be familiar with the gentleman whom I have the QSO with. So I'll leave that up to you. But if you want to know about what makes it tick, then sit back, relax, because here it comes. And here is the really useful rig. And as you can see, it's a tri-band, scratch-built, software-defined radio for SSB, built using the phasing method of SSB modulation, demodulation, which I can say a word about in a moment. Now, as you will see, it's hardly a thing of beauty. But I guess that's in the eye of the beholder, as they say, isn't it? I mean, one thing about it is you can see bits of real radio doing what bits of radio do. You can see all the connections and different things, which is kind of cool in a bit of a kind of open plan kind of way. Just to point out a few of the things on here. So in terms of the controls, on the far left here, this little one here, this is the RF preamp. You obviously got the TFT display here. You'll get a better look at that in a moment. And two little push buttons controls here. These push button controls actually control two of the filters. One is a low pass audio filter, just to remove some of the high frequencies, get rid of some of the hiss, particularly when you're on 80 meters. That can be quite a useful thing. And the other one is to select one of 8 Hilbert transform filters, which are like the software equivalent of a very steep skirted brick wall kind of crystal filter, like you could never actually really build in reality. So that's really useful. So that controls the bandwidth of your transmit and your receive. So that's what those two do. Then you've got the obviously the tuning dial here. This little switch selects the upper sideband if it was in the up position, or the lower sideband as it is there in the lower position, and the speaker facing outwards, which is, I like to do that if I can, if I've got room to do that, rather than having it shooting up in the air, which some rigs have. Then you've got the audio volume control here. Obviously the mic jack. Next to the mic jack, this little switch here, if you switch that down, what that does is it switches off the mic audio input, but it keeps the PTT live, and it switches in the software, in the Teensy microcontroller, which I'll show you in a moment, switches in a sine wave oscillator, so it produces an 800 Hertz tuning tone once you click the PTT. So that's great. So that you don't get any sound actually coming through from the mic, but you key the oscillator by clicking the PTT. This little switch here is purely for firmware updates. It's just a way of switching the audio section out when you update via a USB cable into the Teensy, because otherwise you get a bit of a howl in the audio section if you don't do that. Right. So just a couple more photos so you can kind of see it from different angles. So it doesn't weigh that much, but it is quite bulky. And so that's what it looks like on the inside. Now, the problem, of course, with, as I've said, building a radio in a plastic box is you've got no RF shielding at all. But as you'll see, there is some RF shielding there in the terms of the different little metal tins and things. This big blue tin down the bottom is the bandpass filters, and the kind of tartan tin here are the transmit low pass filters. And you've got the power distribution board here. These are the RF preamps. The actual Teensy is here on the audio board, and you can't see very. There'll be a better photo in a moment, but you'll actually see that the mixer modulator board is here, and the final audio section is over here, and the RF pre-driver and driver here, and that is the power amplifier with the little IRF 510, which doesn't put out much, about 6 watts on 80 meters, and about 3 on 40, and even less on 20. So, some features of the rig. As I said, it's 3 bands of operation. It's got an adjustable RF preamp. It needs that because effectively it's 2 direct conversion receivers, so there's no IF stage, so there's no amplification there. So if you're going to amplify the RF, you've got to do it right at the front end. Now it's got these adjustable Hilbert transform filters, which I've described, which are great. They're mathematical filters. They're filters that also involve phasing, and I'll say a word about that in a moment. And I designed 8 of them, ranging from 2.9 kilohertz right down to 1.5, which is great. So that will control your bandwidth of what you're receiving and listening to, or what you're transmitting. There's also, as I said, an audio low-pass filter built to the same specifications. Lower sideband or upper sideband. It's got a 10 watts audio amp in there. Auto switching bandpass and low pass filters. That is pretty cool. I'll show you that in a moment. So when you make changes to the frequency, the bandpass filters just click in and out. Bright and colourful TFT screen displaying a whopping great 22 kilohertz of bandwidth. SDR Play must be quaking in their boots. Hardly, but that's all right. That's okay. It's because it's an audio board on the Teensy, so it can only actually sample at the maximum, which is CD quality, which is 44.1 kilohertz, and because of the Nyquist frequency, you can only do half of that. So I've only got 22 kilohertz of bandwidth. But hey, it's better than nothing, isn't it? And a nice spectral display and a waterfall. Also got a digital S meter. It's powered by 12 volts and pulls about 2 amps on transmit. And there is a rear PTT jack, so you can connect that to an external linear amplifier, which is what I usually do. Now, the thing about this rig is it is a phasing rig. So, and sometimes people say, well, what is the phasing method? We're more used perhaps to the kind of traditional superhet idea of having a crystal filter, so you might mix your RF down to this intermediate frequency, and you'll amplify it. You might have some automatic gain control on it while it's there, and you will almost certainly filter it. And it's that narrow filter which removes the opposite sideband on either transmit or receive. But with the phasing method, you don't do it like that. And we'll have a look at the architecture of it in a moment. But just to kind of, they say a picture is worth 1,000 words. So I'm going to show you a picture. Well, actually, I'm going to show you 3. Now, what this is just a picture, just to get your head around what's going on. So this is a screen grab from my oscilloscope that I did earlier, and it's just a 1 volt peak to peak sine wave at 7 megahertz. And so just remember that blue trace, because what I also did from the second output of my signal generator, I produced another sine wave, again 1 volt peak to peak, and again at 7 megahertz. But I shifted the phase, and I put the second sine wave 180 degrees out of phase with the first one. So it looks like this. So you've got the first one there, the blue one, and you've got the yellow one, which is 180 degrees out of phase. Now, if you look at them, you'll see that they're opposite. So what I mean is, if you look at the crests, the positive crests of the blue sine wave, they correspond to the negative troughs of the yellow. So actually, if you were to add those, sum them, we would say, together, what you actually get is that. Nothing, basically, bar a little fluctuation, and which kind of makes sense when you think about it, doesn't it? Because you're taking the most positive voltage at a particular point in this wave, and you're summing it with the most negative voltage, and it's the same amplitude of wave, so of course it equals 0, and that is how the phasing is accomplished. It's through basically turning one copy of your signal through 180 degrees so that it cancels out, in our case, the sideband we don't want. And how that's accomplished in the phasing method is in two stages actually. There's an RF phasing of 90 degrees, and that usually happens at the local oscillator, and then there's another 90 degrees phase shift at the audio level as well, and with those two phase shifts you actually get the required 180 degrees. Now it's a bit more complicated than that, as you can probably imagine, but I hope that's helpful. It just kind of gives you, a picture in your mind of what's going on and how it actually works. Right, so there it is again. I've already talked a little bit about some of the things in it, but that's perhaps a bit more of a helpful shot. So you can see now. So down the bottom here, you can see the two SBL1 double balance mixers there, and this whole section actually, this mixer modulator section is two-way. So on receive, it functions as a product detector really, and on transmit it functions as a balanced modulator. And really what we're doing here, as you'll see in a minute, is we've got two back-to-back direct conversion receivers effectively is what we're doing. So you can see some of the things there as we've got them. It looks a little bit different now because I've tidied up some of the cabling a bit to try and reduce any stray RF that might be flying around there. Okay. Right. Okay. So that's the TFT screen, and obviously at the top left here we have the frequency, sideband, and the tuning increment that you're using, and you can vary that so you can tune it as finely as you want. These two figures here, these represent those two red little push buttons that I talked about. So the white figure is the audio low pass filter setting, and the red figure is the Hilbert transform. That's the transmit and receive bandwidth basically. And so you've got a good indication of the signal strength here, and just the noise on the band, and the waterfall here. You get an idea there now why people's signals are, etc. And I put a digital S meter down here as well. It is displaying an S reading, but I quite like the bars going up. And actually, once you get to 9, they all turn red. And I think if it drops below 5, I think they go blue or something. But to be honest, the so much noise locally here, I never get to that kind of stage. But it's all adjustable, so you can tailor it and calibrate it as you like. So let's have a little look at the architecture. So essentially, what happens is on receive, you've got your antenna here. You come to a switching relay. You go through to the switchable bandpass filters, and actually, I'm just going to show you some of these because I'm quite pleased with these. Now, this is actually the low pass filter module, but the switching is identical to both of those and the bandpass filters. So essentially, what's happening? You can see the three filters here: the 80, 40, and the 20 meter filters, and you can see the relays on the end. It's a bit harder to see, but these little black dots here are 2N3904 NPN transistors that are super glued to the relays, and there's one on each one here as well, and then 2 biasing resistors on each bit here, and then these central connectors which come to here and come from these little chop blocks. Now each terminal of this chop block goes to a pin on the Teensy microcontroller. And incidentally, the Teensy is like an Arduino really, but a super powerful, a much quicker version of an Arduino. I refer to it as like an Arduino on steroids. But the Teensy operates at 3.3 volts logic level. So what I've got is I've written some code that looks at what frequency you're tuned to. And if, say, you're on 80 meters, say, and you decide, oh, I wonder what's happening on 40 meters, and you tune to the 40 meter band, what happens is the signal, the 3.3 volts that was on the 80 meters pin and is coming down to here, is stopped, goes to naught, and the 20 meter one stays at naught, but the 40 meter one that now you're on 40 meters goes high to 3.3 volts. And what that effectively does is you put and it's a tiny current through this transistor and this transistor as well. So it's split both ways, goes to both of them. And now that transistor, it's just enough current to turn that transistor on, to switch it on, and its emitter is grounded, and its collector, you can just see, it's hanging off the negative pin, the ground pin of this 12 volt relay, and the positive pin is connected to 12 volts. So what happens is, as soon as a tiny current flows through there and into that transistor, that will effectively switch on that relay and that relay as well. So in that way, you can switch your relays completely in or out of circuit automatically, depending on the software, which is pretty cool. So, and that works really, really well. So you change bands and you just hear all the relays click in, as they do in commercial rigs. Right, let me just go back one. So that's happening here, and it's happening here as well in the low pass filters, and that's what you've just seen. But essentially what happens is you filter your signal, it goes through an RF preamp. As I said, it has to go through an RF preamp because that's the only RF amplification that there is in the rig. Now, it goes then, this is a little transformer, which on receive is a splitter, because you're splitting your RF coming in two ways, and it's a combiner on transmit. We'll get to that in a minute. And so it's going to go, it's going to be split. One signal then goes to this mixer here, one signal goes to this mixer here. We've got an SI5351 little phase lock loop signal generator, which is being controlled by the Teensy. And on one port of the SI5351, it's producing the VFO signal that you want, and on the other one, another port, it's producing the VFO signal that you want, except one port is doing it 90 degrees out of phase with the other port. So this gives you your in phase I and your quadrature Q signals. So what you're basically doing, this is functioning, as I said, like a direct conversion receiver. You're mixing it down to baseband, to audio, and so you've got an audio signal coming out of here now, but there is a 90 degree phase difference now in these audio signals. So they go into the Teensy and they're actually recombined within the software of the Teensy. Also, the other phase shift, the audio phase shift, happens in here. DSP, anything you want, you can edit that audio before you squirt it out, technical RF term, into your audio preamp and your audio power amp and your loudspeaker. Now on a transmit, really it's just the reverse. You get microphone here into the Teensy, no mic amps or anything. You can do all of that in software. So I've got a mic amp, I've got a little bit of compression, I've got a little bit of EQ, all going in there, and then the audio gets the phase shift, 90 degrees phase shift within the software, and then that phase shifted audio comes back out to the mixer, where it gets the phase shifted VFO signal to mix it up to its transmit frequency. It's now combined by that little transformer, gets a bit of RF amplification, is filtered and then goes through to the pre-driver, the driver, and finally your power amplifier, and before it's filtered again by a low-pass filter and out to your antenna. So that's what happens from a hardware point of view. Now, people sometimes say, well, isn't it supposed to be a software-defined radio? There seems to be an awful lot of hardware. Well, there is, and that's because there are different ways of doing SDR. The popular way and the most expensive way, and the way that a lot of commercial expensive SDR rigs go, is to use what's known as a field programmable gate array, which is able to do direct digital conversion. So in other words, to sample a huge chunk of RF directly and then just edit it. But they're quite expensive, and at the moment it's not accessible enough for most amateurs to kind of homebrew in this way. So most of us do this. So this is the other way of doing it, which is basically to mix it down to audio, because when you mix it to audio, it's a lot simpler and cheaper to edit it at an audio level rather than it is to try and do it at an RF level. So that's why there's more hardware than you might expect. So now this is the software architecture. I won't go into too much detail with this because I can feel people glazing over already. But just to say, this top stream here, this is the transmit. So this is all the stuff. In the same way that I've just showed you modules of physical modules, that I built with discrete components. These are digital modules. So they do the same thing, but this is happening within the digital C++ code, which is running on the Teensy, or compiled C++ code. So your microphone sends an input here, and it goes into this audio mixer here, and it could either be switched off if you need the tuning tone, or if not the tuning tone switched off. It goes through these Hilbert filters, and you'll notice that all the Hilbert filters have a plus and a minus 45, and that's because traditionally phasing rigs are very sensitive to balance. This is particularly so in hardware, but that's kind of carried through into the software as well. So rather than just adding a 90-degree phase shift to the audio, which is what we need to do, what we actually do is we add a 45 degree, a plus 45 degree phase shift to one bit of the audio and a minus 45 to the other. So what that in fact does is give you an overall 90 degree phase shift. But it's better to do a little bit on each rather than just on one, if you see what I mean. So so this is the equivalent of your crystal filter, basically, and that's your sideband switch, and that's where you can do that business I was showing you with the 180 degrees to basically cancel out the sideband you don't want, and then that goes to your audio output, and that's your transmitted audio going to the mixer. Let's look at the bottom because that's simpler. On receive, I've got here a very wide Hilbert transform here, very wide, like 22 kilohertz wide, and the reason for that is that my little TFT screen displays 22 kilohertz, and personally I prefer to have the frequency that I'm looking at the hard right on the screen. Because I tend, when I'm looking at 80 meters and 40 meters, to go to the top of the band and work down. Don't ask me why, I just always have. And I'd rather see, if I'm working down from the top of the 80 meters band, say, the 22 kilohertz that's below me that's coming up, rather than the stuff that might be above me. So that's how now the way I achieve that is by mixing that audio signal back up to 22 kilohertz. So it's still the same audio, but it's shifted up, and that's a little sine wave there, and this is a little kind of digital mixer. and that's just for the fast Fourier transforms for the spectral display and the waterfall. What you're listening to is this central bit. So we've got a narrow, what I call a narrow Hilbert transform, and I say one. There's 8 of them that you select which one you want, depending on how narrow you want the bandwidth to be. They're summed together. One bit of it is split off and goes to feed the S meter, and the other bit goes through a low pass filter and out, and then that'll go to your audio stage. So that's basically what's happening in the software.
Filter the noise out to some degree, but if there's someone 1 kc away and he's 25 over, it becomes a wee bit of a challenge. Anyway, Bob, trust you're well, very good evening to you, and hope you've not been eating too many of those mince pies. And John, at some time I've got to tell you about the 303 rifle I sent you an email about, but you know, how the world was running when I was 9 and 10 years old. Anyway, back to you, Bob. G0SYS, correction. G4BGX, over. Yeah, okay, Derek. Well, you're coming up very, very nicely. Amateur Radio Society, 2648 now, signing clear. And wishing everybody very best 7-3. And for those of you that listen, we'll catch you tomorrow on the bubblies. Take care all. Cheers Tony, cheers Glenn. If you're still listening, Henry 73 and anybody else. G4SJY clear. November Yankee. You are that. Why you want X-ray?
Mike 0 November Tango Victor. Mexico 0 November Tango Victor. Thank you very much. You're 59 plus 20. 59 plus 20. Your name here is Nick, November India Charlie Kilo, and QTH is the south coast of the UK. YU1 X-Ray America, Mike 0 November Tango Victor.
Thank you very much for 59 report. Happy New Year. 7-3, bye-bye.
7-3s, bye-bye.
Bye-bye.
Well, I hope that was of interest, and if you do have any questions about the rig, then please shoot me an email to m0ntv@nickthevic.co.uk, and I'll be pleased to hear from you. But until next time, look after yourselves, stay safe. 73s, M0NTV now off and clear. Bye-bye.
I was around there until about 10 years ago now.
Right, well, I left a bit, I think I left, well,